Hello, everyone, and welcome to this second lecture on the reasoning based large language models. If you have missed the first lecture, I strongly recommend you to go back to the introduction video where we have properly introduced the series and how we are going to be structuring this entire course. In today's lecture, we will start with the first method which can be used to impart reasoning capabilities to large language models. Imagine that the time frame that we are starting from is December 22 when GPT 3.5 was released first. Remember that it was made to answer like humans, but it was not made to think like humans. It was not a reasoning large language model. Slowly from there on, we have come to a stage where we have large language models that can actually reason, that can give you the series of steps which they go through before they give you the final answer. OpenAI's Owen model was the first reasoning-based model. After that, there have been a number of reasoning-based LLMs which have come into the picture. For example, DeepSeek R1. So, whenever you are listening to this lecture, keep in mind that the time frame is 2022 onwards, because that is the time after which people started to think about reasoning-based LLM seriously. And nowadays, a lot of companies and almost all LLM providers have a reasoning LLM in their armory. Okay, so now we are going to cover method number one, which is inference time compute scaling. So let us understand what is inference time compute scaling. Uh, all of us are humans, and we know that we tend to give better answers when we think about the answer for more time. Remember, when you're writing an exam, sometimes you are stuck in a question because it involves layers of thoughts. Only after you spend enough time on that problem are you able to answer the question correctly. Some other examples of these type of problems where more thinking is required is complex maths problems or even puzzles like Sudoku. I'm sure all of us have played some kind of crossword puzzles which appear in newspapers. Well, you can't answer all the puzzles at once, right? There are some horizontal answers, there are some vertical answers, and many of them are connected with each other. So, unless you have an idea of all the clues in the horizontal and vertical columns, you will not be able to fill each and every single entry in the crossword puzzle. Another example is of a mathematical problem where we ask the question: are the number of prime numbers finite or infinite? This is also not very easy to answer, and it is probably going to require a fair amount of thought before you come to the answer. Let's think of chess. Chess is an example where whenever a player makes a move, the move is never made immediately. You might have seen matches where grandmasters are playing against each other, and sometimes they take tens or 20 minutes or even more than that to play their next move. Why? Because they are thinking through all possible scenarios before they make their next move. So generally we have observed that as humans, when we think more about a problem, we tend to come to the correct answer. Now similarly we apply the same logic to large language models, and we ask the question: what will happen if large language models think more before they give you an answer? Just pause here for some time before you proceed with the video, and try to answer this question. Do you think LLMs will give a better answer if you just ask them to spend more time before they give you the answer? That is a very interesting question, and we are going to find out the answer soon in this lecture. Let us take a very simple example. Roger has five tennis balls and he buys two more cans of tennis balls. Each can has three tennis balls each, and the question we are asking is, how many tennis balls does he have now? Now, let's look at the answer given by a regular LLM over here. So you can see that when a regular LLM tries to answer this question, the answer it gives is answer is 11, which is in fact the correct answer, and the number of tokens it uses is only 3. Now we will force the model to think more before the model gives an answer. So instead of directly giving the answer, which is 11, the reasoning based large language model comes up with a series of steps. The first step is Roger started with 5 balls. This step uses 4 tokens. The second step is 2 cans of 3 tennis balls, each is 6 tennis balls. This step uses 11 tokens. And the last step is 5 plus 6 equal to 11. This step uses 5 tokens. So when we ask the model to think more, it certainly uses more number of tokens before it gives you the answer. So this is called as test time compute. The amount of computational resources the model uses before it gives you an answer is called as test time compute, which is illustrated in this figure. From the above example, you can clearly see that reasoning based LLMs uh, have significantly higher test time compute compared to regular LLMs. Almost it's 3 and 23, so it's maybe somewhere between 7 to 8 times. But why are we spending so much compute in the testing time? How does that make sense? Because in the previous example, even the accuracy stayed the same. Both the LLMs gave the correct answer, anyways. Well, it turns out that if you spend more computation resources in the testing time and you ask the model to think more, the model starts to reason for other questions as well, and the accuracy of the model significantly improves. And this is what we'll be looking at in detail in the remainder of this course. The main thing which we'll look at is why does allocating more computation resources in testing uh, help increase the accuracy of the model to answer complex reasoning based questions, which is very similar to what happens in the case of humans, right? Humans also tend to give better answers when they think more about a problem. It turns out that exact same thing happens with large language models as well. In this picture, you can see that in reasoning based LLMs, there is a significant computational resources being used in the inference, which I will mark with my pen over here. And in the regular LLMs, inference happen pretty much instantaneously. It's very fast. And there is a reason why people do this. The reason is that we see a scaling which looks like this. As the test time compute increases, the accuracy of the model also typically tends to increase. There are a lot of nuances when I say this sentence. However, I want you to get an idea of why is the word scaling in inference time compute scaling. The reason is that as you increase the number of resources, uh, computation resources in the testing time, we see that the accuracy of the large language model typically tends to increase. We will look at more nuances about this statement as we follow this lecture. Okay, so this sounds quite intuitive, right? Giving more time to thinking leads to a better answer. When did we think of all of this? So the first paper which came out, which showed that if you tell an LLM, if you give an LLM a series of prompts where they are not just input output prompts, but you have given them a chain of thought which links the input to the output, then the LLM learns to reason for all other prompts which are not given in the example prompts by the user. So have a look at what they say in the paper. We explore how generating a chain of thought, which is a series of intermediate reasoning steps, significantly improves the ability of LLMs to perform complex reasoning. So what does this mean? We are evaluating large language models on the ability to perform complex reasoning tasks. And it turns out that uh, if you ask the LLM to generate a series of thought before it gives you the final answer, the accuracy on these complex reasoning tasks also increases. So, in particular, we show that how reasoning abilities emerge naturally in sufficiently large language models via a simple method called chain of thought prompting. So, this is the first technique that we are going to learn, which is called as chain of thought reasoning. This paper came out in the year 2022 and it was released by the Brain team at Google Research. This work primarily showed that reasoning abilities in a large language model can be unlocked by two main ideas. Idea number one is that arithmetic reasoning can benefit from generating natural language rationales that lead to the final answer. So these words I know sound a bit complicated, but natural language rationales mean the series of steps which take you from the question to the answer. And idea number two is that we can do this by simply prompting the LLMs. So we don't change anything with the model weights, we don't change anything in the model architecture. The LLM stays the same, the brain stays the same. We just prompt the LLM with a chain of thought by using a series of input output examples. And then through this prompting, the LLM will learn to answer in a similar way to other complex reasoning tasks which we ask it, which are different from the initial input output examples which we are giving. So let's try to understand what I meant by that. Instead of fine tuning a model, one can simply provide the model with a few input output examples demonstrating the task. Now remember that when you are actually asking a complex puzzle, let's say I am asking the LLM to solve a Sudoku. At that time, I am not giving the input output examples. This is given beforehand to the large language model only once. Let's say there are a series of 20 input output example pairs which we are giving to the large language model. That's all. And then whenever we ask a new problem like a Sudoku examples, the large language models knows that okay, so uh, I should answer this in a similar way as the input output examples. So if in the input output example you have included a series of thoughts, maybe I should answer the final Sudoku puzzle also in a similar way. Let us try to understand and look at some practical examples later on as well. So, what is chain of thought prompting? Have a look at the difference between these two. So, here, this is one input example, input output pair. This is the input and this is the output. So, the input is the same example which we asked before, in which Roger has 5 tennis balls and he buys two more cans of 3 tennis balls. Now, in the output, we don't directly write the answer is 11. But in the output, what we write is we write all the series of steps that are required to come up with the answer. For example, step number one is Roger started with 5 balls. Step number two is two cans of 3 tennis balls, each is 6 balls. Step number three is 5 plus 6 equal to 11. And step number four is the answer is 11. So there are four steps which I have explicitly mentioned in the output. This is called as chain of thought prompting. So let us look at this example again. Here, what you can see is that there are four thoughts which are linked with each other. As I've shown in this figure, thought number one, thought number two, thought number three, and thought number four. And these four thoughts are linked with each other. That is why it is called as a chain of thought. And then what you observe is that once you give a chain of thought, the model tends to answer to other inputs also in a similar way. For example, Let's say you have given this in one of the example in the input output prompts. Now if you ask a question which is a new question, let's say cafeteria has 23 apples and if they use 20 to make lunch and bought 6 more, how many apples do they have? So the model learns to think in a similar way for new input examples as well. For example, you can see here that the model output is the cafeteria had 23 apples originally. They used 20 to make lunch, so they had 23 minus 20 equal to 3. They brought 6 more apples, so they have 3 plus 6 equal to 9. The answer is 9. And in the standard prompting, the answer it gives is 27, which is the wrong answer. Now, okay, so it turns out that this paper now has 12,000 plus citations. Uh, uh, so far, we have understood that, okay, so what this paper has taught us is that it has taught us that introducing chain of thought in the input output prompts helps the model to reason well for complex reasoning tasks, right? But then, how come so many citations? 12,000 is a huge number, right? Are we really understanding the importance of this paper? So, let's look at the contributions, right? The first contribution is sufficiently large language models. Sufficiently large models can generate chains of thought if demonstrations of chain of thought reasoning are provided in the examples of few short prompting. So, what does this statement mean? This is an example of a demonstration of a chain of thought prompt. So, if the model is provided with examples of these demonstrations, maybe 10 or 20 demonstrations, then the model actually can generate chains of thoughts for new questions, new reasoning questions also. So, again, try to read this statement now. Sufficiently large models can generate chains of thought if demonstrations of chains of thought reasoning, which are the input output examples, are provided in the examples of few short prompting. So, this is a new word which I have not introduced before. It says few short prompting. So, few short prompting is the practice of providing a number of input output examples in the prompt. So, for example, this is one example of input output, right? This is one example. Similar to this, you might provide 10 more examples in the input output prompt. This method of providing multiple examples in the input output prompt to kind of guide the LLM or nudge the LLM towards the answer, or to nudge the LLM to understand how are we expecting the output, in what format we are expecting the output. That is called as few short prompting. Why few? Because we are providing a number of input output examples. Uh, okay, so you can notice here that this statement also mentions sufficiently large models. What does this mean? What do I mean by sufficiently large models? I will come to that eventually. And the paper evaluated the performance of the technique for three different reasoning tasks. One is arithmetic reasoning tasks, second is common sense reasoning tasks, and third is symbolic reasoning tasks. By the end of this lecture, uh, you should be clear with respect to the difference between arithmetic, common sense, and symbolic reasoning tasks. We need to understand the difference between these three. Okay, so few short prompting, remember, had already existed before. People were already providing input output examples in the prompt. That paper came out in the year 2020 actually, where few short prompting was actually released. So let's try to look at that paper, few short prompting, foundational paper. This is the paper which I am talking about. So This paper came out in 2020, and there they introduced uh, a few shot prompting technique. However, uh, they did not talk about chain of thought, which means that all the examples which they included in the input output examples, they looked like this: question and directly the answer. It did not include the chain of thought which leads to the answer. That was the main contribution of the chain of thought reasoning paper. Now let's look at the different examples in the chain of thought reasoning which can be used in the prompts. uh, I have talked several times about different kinds of examples to be given to the large language model in the prompting step itself, maybe 10 or 20 examples with a chain of thought. So let's look at some other examples. The first example we have already looked at. Let's look at an example in the common sense category. Sammy wanted to go to where the people were. Where might he go? Options are racetrack, populated areas, desert, apartment, roadblock. So the answer that we give in the prompt is the answer must be a place with a lot of people. Racetracks, desert apartments, and roadblocks don't have a lot of people, but populated areas do. So the answer is B. So here you can see the chain of thought which we are mentioning in the prompt before we give the final answer. We are not directly mentioning the final answer over here. Let's look at another example which is in the symbolic reasoning category. A coin is heads up. Mabel flips the coin. Shalonda does not flip the coin. Is the coin still heads up? The coin was flipped by Mabel, so the coin was flipped one time, which is an odd number. The coin started heads up, so after an odd number of flips, it will be tails up, so the answer is no. So here also we are asked a question and then we know the answer, but we are not only giving the answer, we are giving the chain of thought which leads the LLM to the answer. So these are the number of different input output examples which are given in the prompt through which the LLM can understand that okay, maybe the user wants me to not directly give an answer but to think of the steps before I give the answer. And this small nudge actually improves the accuracy of the LLM in complex reasoning tasks dramatically. And that's the reason why this paper has more than 12,000 citations. Often concepts which appear simple, they are not very simple to conceive, and these are the concepts which have the broadest of utility. And chain of thought reasoning, I believe, is one such concepts with a concept with a massive utility and very simple to understand because all of us think uh, like a chain of thought reasoning. So we all of us understand this technique very intuitively. Okay, so it was a very simple idea, but let's look at the kind of results that they got. Now, whenever you go through any LLM paper, you will see a bunch of results, and I want you to also understand how to read these results properly. This is one of the graphs which they got in the paper. The first question we ask is okay, which is the large language model which they are using when they get this graph? So, the large language model is called as PALM. In case you are not aware of PALM model, PALM is a large language model which is released by Google, and it is it comes in different sizes. The maximum size is 540 billion parameter. Okay, so they have used a PALM model, and what is this study telling us? So this study tells us that on the x-axis you have scale, right? So as we increase the number of parameters, which is on the x-axis, on the y-axis you see the accuracy. Whenever you see an accuracy metric, you should always ask the question that on which data set is this accuracy calculated. So this accuracy is calculated for a GSM 8K dataset. GSM 8K is a arithmetic reasoning dataset with a bunch of arithmetic reasoning questions, GSM 8K dataset. We are going to look at a project after this course where we will understand the different questions which are asked in this dataset. Typically, the questions are something like this. Let's say Natalia sold clips to 48 of her friends in April, and then she sold half of that many clips in May. How many clips did Natalia sell altogether in April and May? So we know the answer is 48 plus 24, which is 72. So the Palm model was given a bunch of questions from the GSM 8K dataset, and then the accuracy was evaluated on that dataset. How was the accuracy calculated? How many questions was the LLM able to answer correctly? Now, let's look at standard prompting first. We see that the accuracy of standard prompting is really low, but as soon as you introduce chain of thought prompting, the accuracy significantly increases. You know, there is a big gap between standard prompting and chain of thought prompting. Okay, that is the first observation. Can you observe anything else from this figure? The second thing I can observe is that the accuracy of the chain of thought prompting actually increases with the scale of the model, which means that bigger and bigger models are very good at reasoning and they have very good accuracy. Okay, that is fine. Any more observations from this graph? Well, I can see one more thing from this graph. If you look at very large palm models, they are almost comparable with the best supervised fine-tune models, which means that without going through the computationally expensive uh, task of supervised fine-tuning, we can still achieve the same accuracy on the arithmetic reasoning data set uh, by simply using a prompting technique, which is the chain of thought prompting. Okay, so we have observed three different observations. First is that chain of thought prompting compares significantly well with respect to standard prompting. Second is that the accuracy increases with the scale of the model. And third is that for very large palm models, the accuracy is almost comparable with supervised fine tuning. Okay, in case you're not familiar with supervised fine tuning, it's the process of, let's say, you have a pre trained large language model, and then you have an additional data set of input output pairs, which you again use to train the model. So that is called as the step of fine tuning. It is usually computationally expensive, but it improves the LLM significantly. Now, here what we see is that we achieve an accuracy which is similar to that of supervised fine tuning without through the computationally expensive task of the fine tuning process. Okay, so as we noted, there are three observations here. Accuracy is low for small models. For higher models, accuracy is comparable to supervised fine tuning. The second observation is that chain of thought prompting outperforms standard prompting on the arithmetic data set concerned. And the last observation, which is very interesting, is that chain of thought reasoning is an emergent ability of increasing model scale. This is something which is mentioned multiple times in this paper, and I want to highlight this statement because I think it is pretty significant. I think what this statement means is that as you increase the model size and you try to nudge the model in the direction of chain of thought reasoning, the model is able to understand that nudge much better and is able to give you answers which are aligned with that nudge, which smaller models simply don't capture. And the way I think about it is that if you have a person who has a small brain, let's say a person who is not very intelligent, right? Who is not good at uh, uh, grasping concepts. Now, even if you try to nudge this person in the direction of reasoning, they are never going to get it, as opposed to a person who has a refined brain and who has a brain with an ability to grasp concepts easily. Now, such a person, a small nudge is going to be sufficient to understand what is expected for complex reasoning tasks. And that is exactly what is happening in the case of these large language models, which is very interesting to note. And in this paper, there is also an analysis of why does the model scale improve the chain of thought prompting. And you can clearly see that here they have analyzed three different types of problems: semantic understanding, one step missing, and the third type of problem. Uh, so, what we can see is that as you increase the model, as you scale the model from 62 billion to 540 billion parameters, these are the errors which are fixed by the model. So the model starts to fix errors which the smaller models were initially making. And that is because the model is understanding the nudge which has been given in the prompting stage itself. So it's able to answer these questions in a much better way compared to the smaller models. And this is one outcome which I want all of you to remember. Okay, chain of thought reasoning is incredibly effective compared to standard prompting. We have understood that. But it's not very effective for very small models. It's only effective for large models where reasoning is an emergent ability, where the model understands the nudge much, much better. Okay, so here is an example of how the larger models gives correct answer compared to the smaller models. The question we are asking is that Tracy is using a piece of wire which is 4 feet long, and the wire was cut into six pieces 6 inches long. Okay, how many pieces did she obtain? So we know that 1 feet is 12 inches. So let's see. Okay, so totally there are 4 into 12, which is 48 inches, and then the number of pieces are 48 divided by 6, which is 8, which the larger model answers quite correctly, but the smaller model gets confused. It actually just multiplies 4 into 6 and gives the answer as 28. So this is a semantic understanding error which is fixed in the larger model. This is one example out of all these examples which have been highlighted in the previous figure. Okay, now I hope all of you have understood how chain of thought reasoning works very effectively for arithmetic reasoning tasks. But what about common sense reasoning and symbolic reasoning tasks? Is it that effective, or it's not very effective? Let's understand. Firstly, common sense reasoning. I had given an example previously also. Here, if you look at it, we had looked at an example of common sense reasoning. Another example is would a steel ball sink in water? So even for common sense reasoning, from these figures, you can see that chain of thought prompting always outperforms standard prompting, although the difference is not very high for CSQA. But for all other examples, especially for sports related questions, the difference is huge. And here it outperforms human level performance as well. And then we come to symbolic reasoning. Symbolic reasoning is an interesting terminology because it is used to define problems like these. A coin is heads up. Akshay flips the coin. Deepti does not flip the coin. Is the coin still heads up? So we know the answer is false to this, right? Because now we know that the coin is tails up. But it turns out that LLMs are not very good in answering these symbolic reasoning type of questions, and they make errors. And that is why it is important for us to understand how well an LLM is performing on symbolic reasoning tasks as well. And here also you can see that chain of thought prompting significantly outperforms standard prompting. The main result from this study is that chain of thought prompting works very well in arithmetic, common sense, and symbolic reasoning tasks. So now we are going to go ahead and we are going to look at technique number two, which is zero shot reasoning. Before we go ahead, I want all of you to take a step back, pause, look at whatever we have looked at so far. Also, look at the corresponding paper which we have referenced in this study. Make sure you have understood all the concepts. Then we'll move to zero shot reasoning. And then finally, we'll do some hands on projects. And in the hands on projects, we'll look at all the nuances that we have talked about in the lecture, which will give you a practical understanding of how inference type compute scaling is really implemented in practice. Okay, so we are going to look at technique number two now in the method of inference time compute scaling, which is zero shot reasoning. Uh, and this method is even more simpler than chain of thought reasoning. So let's take an example of a statement. Ira, go and study in your room. You have to write the table of nine. Make sure to think step by step. This simple prompt to a person makes them understand that they should think step by step before they come to the answer. This exact same logic was used by the authors of the zero shot reasoning paper. Let's take an example. So, firstly, plain zero shot. The meaning of zero shot is, if you remember what I explained before about few shot prompting, that we provide a series of input output examples in the prompting stage. Zero shot means that we provide absolutely no examples in the prompting stage at all. That is, we provide zero examples. So this is simple zero shot where there is a question and then there is no example provided here. As you can see here, the answer is blank. And then this is the output, which is wrong over here since it should be 16 divided by 2 divided by 2, which is 4. Now, in this paper, they introduced zero shot chain of thought, which means that we still have zero examples as input output pairs, but instead of that, we only write this let's think step by step, which is very similar to the example of ERA, which I talked about before. So, what happens here is that the question stays the same, but instead of providing an answer in the prompt, we just add a sentence which says, let's think step by step. And then, interestingly enough, the model learns to reason. So, how is this different from plain chain of thought or few shot chain of thought? In the example of chain of thought reasoning that we looked at before, we provided an input output examples where we told the model that if this is the input, you should reason and then you should provide the output. Now, here we are saying that, okay, we are lazy to do all of that. But all I want to do is that I just want to add a sentence which says, let's think step by step. And then the model learns to reason on its own. That's all. So, why zero in the name? It's because we are not giving any input output examples in the prompt. Now, what is mentioned in the paper is that uh, they are prompting the LLM twice in this example. The first prompt is where they ask, let's think step by step, which we looked at before. Then we get an answer from the LLM. Then that answer is passed back to the LLM. And then we also give another prompt which says, therefore, the answer is. Okay, so here, what will be the final answer? The final answer will be this, which is the first answer provided by the LLM. And then after that, therefore, the answer is 375. So they extract the answer in two steps. And they obtain fantastic results. You can see from the graph that zero shot chain of thought significantly outperforms zero shot reasoning. And now you can read these plots as well. This is very similar to the plots which we had in the chain of thought example. Here the model is the palm model, The data set which we are using is the arithmetic reasoning data set, which is the GSM 8K data set. And here also you can see that zero shot chain of thought significantly outperforms zero shot for very big models, that is for 540 billion parameter models. So larger scale models exhibit better reasoning. Remind you of anything? This is very similar to our observation in the chain of thought reasoning case as well. Okay, so today we discussed two techniques. One is few shot chain of thought or simple chain of thought reasoning. And secondly, we discussed zero shot chain of thought, which means that we are not going to provide any input output examples, but we are only going to tell the large language model to think step by step. Now, in the last part of this lecture, we are going to look at two hands-on projects. And these projects I have specifically designed for all the students who might be having the question that where do I exactly specify these input output example prompts? I had the same question when I read the original chain of thought prompt paper. I was confused that where do I write these input output examples and what do they actually mean? So, whenever we are going to look at projects in these courses or in this course, we are going to look at specific problem statement which are going to help us understand something on a deeper level. So, we are going to probe some questions. For example, in project 1, we are going to understand that can we evaluate the effect of model size on chain of thought reasoning by ourselves. Okay, so we are going to understand how does model size affect the chain of thought reasoning. We are going to consider small models for this. It takes significantly high time to evaluate on larger models. The models which we have considered are Flan T5 small, Flan T5 base, Flan T5 large, Tiny Llama 5.2 and Zephyr 7 billion model. As you can see, the number of parameters are varying from 80 million to 50 million, right up to 7 billion parameters. The data set which we are considering is GSM 8K, which is the arithmetic reasoning data set. Okay, before we get into the hands-on demo, I want all of you to stop this video and make some predictions. How do you think these models will perform on this data set if we use chain of thought reasoning? What kind of answers will they give? Will they give correct answers or will they give wrong answers? Now let's dive right into the projects. Okay, so the first project we are going to look at is this, which is Module 1, Inference-Time Compute Scaling, Effect of Model Size on Accuracy with Chain of Thought Reasoning. I am going to share all these Colab files with you in the chat so you can follow as I'm speaking by interacting with these notebooks. The first step is installing the dependencies, which are transformers, datasets, and accelerate in this case. In the second step, we are going to load the GSM 8K dataset over here, and we have extracted 50 examples from it, as you can see. You can ignore this swarm dataset for now. This is an exploration phase where I was exploring with multiple datasets, including the GSM 8K as well as the swarm dataset. Now, this is where we define the chain of thought prompts, which are the input output examples which we are going to provide to the model. There are three examples which I have considered here. The first example is Emily has three apples. Her friend gives her two more. How many apples does Emily have now? And the answer we have given is Emily starts with three apples. Her friend gives her two more. So 3 plus 2 equal to 5. The answer is 5. Similarly, like this, I have provided three examples. Then here I have written a function which can be used to evaluate the models. Is my model giving a correct answer on the GSM 8K dataset or not? And then finally, I will plot. As you can see here, I have taken these three different models. Uh, I always choose models which are open source and There is no gating restriction from Hugging Face, so it becomes very easy to use them in Google Colab. This is the plot which I got. The accuracy of all these models, as you can see, is not very high. It is in fact very, very low, but it does increase with the model size slightly. Now, why am I getting accuracy which is bad, which is not very high? Is it consistent with the results which are obtained in the paper? Let's have a look. Let's see. Firstly, let's try to see the actual results which are given by our model to get some understanding, right? Okay. The first question is Janet's ducks lay 16 eggs per day. She eats three for breakfast every morning and bakes muffins for her friends every day with four. She sells the remainder for $2 per egg. How much dollar does she make? And the correct answer is 18, but our model gives 12. Similarly, in example 2, the correct answer is 3, but our model gives 10. You can see all of these are very practical examples which require some sort of arithmetic reasoning. And we have compared the actual answer with the answer which our model is giving in this output. Okay, so why does our model perform low? From these graphs, you can see that we are somewhere in this category, which is the initial part of the x-axis. And you can see from here that the accuracy is almost between 0 to 5%. Even up till 8 billion parameters, it only increases above maybe 20, 30, 100 billion parameters. So what we get is absolutely consistent with the results which we obtain from the paper also. Chain of thought reasoning is in fact incredibly effective for only larger models. In our case, we are using smaller scale models. That's why the accuracy that we get from these models is not very high. Okay, so let's try to see what will happen if I use bigger models instead, right? So now in the next part of the code, I have used bigger models in which these are the three models I've used. Zephyr 7 billion parameter Phi 2, which is 2.5 billion, and Tiny Llama, which is 1.1 billion. And here are some examples which I get. So you can see that correct answer 18 and our model is giving 300. So model does not give correct answer even for the higher scale models. And this is the comparison of all six models on the few short chain of thought reasoning which we have implemented. So what did we learn? Chain of thought reasoning is only effective for very big models, not for the models we are considering here. This is in fact consistent with the results which we see from the paper as well. The model starts to give reasoning steps if input output chain of thought examples are provided. Yes, this was a very interesting observation. As you can see in the model output, our model is giving a series of steps. That means that by it understands the initial nudge which we have provided over here. This was the nudge that we provided to the model here. And then it understands to reason that, okay, even if the answer is wrong, but it still attempts to reason before it comes to the final answer. I want all of you to go ahead and implement this notebook and try to see these differences and answers you are getting by yourself. I have subscribed to Google Colab Pro, as you can see here, so it allows me to run on A100, but you can use a T4 GPU as well. The second hands-on project which we are going to look at is we are going to compare three different methods. Few shot prompting, that is without chain of thought. This is going to be our baseline. And on top of that, we are going to add few shot chain of thought prompting and zero shot chain of thought prompting. We are going to compare these three. We are going to use Phi 2 and Zephyr 7 billion parameter model for these comparisons, and the data set that we are going to use are the logical and symbolic reasoning tasks related data set. So let's have a look at this notebook. Again, this file will be shared with you, so don't worry. The first step is to install dependencies. Next, we are going to load the model. We are using Microsoft Phi 2 model over here. And here are the mixed reasoning questions, logical plus symbolic, which I have defined over here. You can see that they are very different from the previous arithmetic examples which I had. And then these are the few short chain of thought prompt, and then just the few short prompt, which is the baseline where you directly see that only the answer is given here, right? You don't give the chain of thought like you do over here. And then we go down and we run the models. You can see that for zero shot, we have only given let's think step by step, which is what I mentioned before from the Miro board as well. And then this is the display that I get for these five questions. So when you look at this table closely, you can actually pause on this video and look at it. You see that only zero shot chain of thought is more effective compared to the others. We also evaluate the accuracy in a quantitative way where you see that zero shot accuracy is 20%, whereas the other methods is almost 0%. So I was wondering that why is few shot COT and few shot no COT giving such a low accuracy and very random answers, right? And I tried to see whether adding more prompt examples made sense. So we have given five examples before. I tried to see if we add 10. And then I also tried with a different model, with a higher model, and tried to see whether that makes a difference. So it turned out that even in that case, the answers which you, okay, so these are the answers which you get for, for giving 10 examples. And even here, zero shot COT is very effective, and even for the higher models which I used, which is the Zephyr 7 billion parameter model. So zero shot COT is effective compared to other methods. That is my conclusion from this analysis. Although we are not looking at models more than 7 billion parameters, for which might be all these three methods are very effective as you see from the graphs. But from a point of view of academic study, to understand the nuances, the differences between these three approaches, it is very important for you to implement this notebook and see how the model learns to reason. You can see here that just by giving let's think step by step, it actually learns to understand correctly. For example, a train travels 60 kilometer for 3 hours. How far does it go? To find the distance, we multiply speed by time. So the train goes 60 into 3, which is 180 kilometers. The answer is 180 kilometers. Okay, so all of you just implement this second notebook as well. The final notebook which I want to share with you is from a LinkedIn post I saw from Sebastian Rashka, where he implemented a Llama 3.2 completely from scratch. What does from scratch mean? From these, in these other examples, you can see that I am, importing the models from somewhere or the other. Uh, so you can see here that, okay, so I'm loading the model from somewhere, right? From Hugging Face. But here, the entire script is within my control. I'm not loading the model from anywhere, which is hosted on Hugging Face entirely. So it's like an LLM is built from scratch. Llama 3.2 is built from scratch, and I wanted to just experiment with it a little bit. So you can see here, if I give the input as, okay, so the input is here. What do llamas eat? And the output is over here at the bottom. Llamas are herbivores, which means that. And this only works well for 3 billion parameters. I noticed. If you use 1 billion parameter model, it doesn't work that well. So there is a feeling of satisfaction when you implement this notebook, when you feel that you have implemented the LLM from scratch, although the code was not written by you. But our objective is then to apply uh, zero shot prompting, zero shot reasoning, chain of thought reasoning over here, and try to see how the model performs on common sense reasoning and simple arithmetic tasks. So this is another interesting homework for all of you, which will give you an understanding of implementing chain of thought prompts on not models which are hosted somewhere, but by on models which are built from scratch, and how well do they perform. This is a very fertile ground for experiments, understanding, and building intuition. Okay, so with this, let us conclude our lecture. I hope this lecture was very interesting for all of you. And in the next lecture, we will continue to discuss about module 1, which is inference time compute scaling. Thank you very much, everyone. Have a good day.